So what I'm going to do here is to show you an example, maybe more than one, of how to predict products and the driving force for a double replacement reaction. With a double replacement reaction, it's a bit different from single replacement in that with single replacement, you can tell without even predicting the products whether there's a driving force. The driving force for single replacement reactions comes from the fact that the element that's by itself is more active. And more active we know because it's higher on the activity series than an element it is like in a compound. With a double replacement reaction, we first have to predict the products to see if there is a driving force. There are three driving forces. One is the formation of water, which we usually write as HOH when we're predicting products. The formation of a gas, although in this class you won't have to worry about that. We don't get into any equations with gas products and double replacement reactions at this level. And the last driving force is the formation of a solid. And this is where we'll be spending most of our time trying to figure out whether we have a driving force, the formation of a solid. Although sometimes we'll have the formation of water. One thing that you need to know is that the formation of water occurs whenever there's the subcategory of a double replacement reaction, that subcategory being an acid-base reaction. Okay, so first thing I want to do is to figure out whether what the products are. I'm going to look here at this equation, and I can see that I have a polyatomic ion right here. And there are two clues. One clue is this NO sub 3 is in a parentheses. The only reason we use parentheses in balancing formulas is when you have a polyatomic ion. But even if there wasn't a parentheses there, you can see that there are 1, 2, 3 elements. And anytime there are 3 elements, or more than 3 elements, you're going to go to the common ions list and see if you can find any polyatomic ions that match what's in there. And if you look at the common ions list and search around carefully, you'll find NO3 1 negative. That's a nitrate ion. So this is confirmed that it's a polyatomic ion. So this would be part of the reaction, part of the formula, one part, and this is the other part. It's a 2-part formula. The lead on the front is a part, the nitrate on the back is a part. And this one pretty clearly is 2 parts. You've got a metal, sodium, and a non-metal. This is an ionic compound, and it's in 2 parts, sodium iodide. So when we have two 2-part formulas like this, the first thing we want to do is to predict that these 2 parts are going to exchange places. The front part of one of the first compound in this case will go with the back part of this one, and the front part of this will go with the back part of this one. And it doesn't really matter whether you write NaNO3 first or PBI first. It doesn't matter. What I want to do is just simply put the front parts with the back parts as products over here. So I'm going to write PB and I on this side. I'm not going to balance the formula yet, but it's very important to know that you have to balance the formula before balancing the equation. Then I'm going to put Na and NO3 together. All right, so before I do anything else, I want to see what physical states can I assign to these 2 compounds. I don't have water here. I don't have HOH, so that's not going to be a liquid. That's the only liquid we're going to worry about here in double replacement reactions. There's no gas, as we said, in any of the reactions we're going to work with. So I want to find out if either of these is going to be a solid, and well, actually I want to find out the physical state of both of these. What I didn't tell you was that this is going to take place in an aqueous environment. That's something you need to know in order to actually write all the physical states for this. So let me just pencil in down over here on the side. In an aqueous environment. That means there's water, that these chemicals are in water. So what another physical state, particularly of these 2 things, because that's going to tell us if there's a driving force. For that, we're going to need the solubility rules. Solubility rules are found on your test references, and it looks like this. If you don't already have out your test references, looking up polyatomic ions get out your test references and find the solubility rules. And I'm going to ask the teacher to pause this video if you need to wait on students to get out their solubility rules. Okay, so what I want to do is to find one or the other part of this compound. So I'm going to search through all this, and I can see here in the second solubility rule, chlorides, bromides, and iodides. Well, that's iodine, and iodine, when it's a negative ion, or on the back of a formula, is an iodide. So this is the rule that's going to apply to this compound. It says all iodides, except silver, lead, and mercury 1, are soluble. Soluble means if there's water around, it will dissolve in water. If this is an exception, lead, and Pb is lead, you got to know what the name of the symbol is here. So if you don't know, look it up. That's what your periodic table is for. And that's also in your test references. So you find Pb and see that it's lead. Okay? So since most iodides are soluble, except for, in this case, lead, if it's not soluble, it's insoluble. When there's an aqueous environment, insoluble means it's a solid. Okay, let me repeat that. In an aqueous environment, if a compound like iodides are soluble, they also would be aqueous. But if iodides are combined with something that's an exception, in this case lead is an exception, then the compound is going to be the opposite of soluble, which means insoluble, and insoluble when in an aqueous environment means it's a solid. Well, there's our driving force. There is a driving force for this reaction, that driving force being the formation of a solid or precipitate in an aqueous environment. So let's find out what the physical states of these others are. If I look right here in the very first of the solubility rules, I'll see that nitrates, and that's a nitrate, are all soluble, and there are no exceptions. Soluble means when you're in an aqueous environment, it means that's going to be aqueous. Iodides, we just got through saying that iodides are soluble. Sodium is not one of these three exceptions, silver, lead, and mercury, so this must also be aqueous. However, if we look at the very first rule, it says group 1 salts. Well, this is a group 1 salt. What that means is that the first element in the formula is in group 1. Well, group 1 is column 1 of the periodic table, and sodium is in column 1. So you have two rules now that apply to this, indicating that this is going to be a soluble substance. We're in an aqueous environment, so this is aqueous. All right? Over here, nitrates, we said all nitrates a moment ago. In the very first rule, all nitrates are soluble. And if you read the rule carefully, please take the time to read the rule. There are no exceptions, so this must be aqueous. All right, but we do have a driving force. If we have a driving force, the reaction occurs. And now we have to balance the formulas and then the equation. So you can assume that these were already balanced because I already had this subscript here. But we need to figure out what this is going to be, what this balance is going to be. So I'm going to move down a little bit because I want to save room for the atom inventory in here. Let's put PBI. Okay? PB, we look it up on the periodic table with oxidation numbers. And we see that PB has more than one oxidation number. Has a 4+ and a 2+. We need to know which one it is, and right now we don't know. And we're going to put it together with iodine. And iodine, if this is going to be some kind of a plus charge, and the only charges we have for lead were 4+ and 2+, it's a plus charge. In order to get a neutral compound, this one has to be negative. So when we look at the possible oxidation numbers for iodine, if you aren't looking at your periodic table with oxidation numbers, you need to get it out and look with me. there's only one negative number. So this must be a one negative charge on the iodine. All right, so how are we going to figure out what the charge on the lead is? Since there's nothing here to tell us whether it's 4 plus or 2 plus, we go back over here and find out what the charge was on this side. So here's our lead on this side. We want to find its charge number. We're putting that together with 2 nitrates. This subscript 2 after the parentheses means I have 2 of everything inside, so I have 2 nitrates. Go to your common ions list, find nitrate, and you'll see that nitrate has a 1 negative charge. 1 negative charge, and there are 2 of these. Okay? We want all the charges to equal out to 0. So we don't yet know what the charge is on lead. We know we do have just 1 lead. We don't know the charge. We're putting that together with 2 particles of nitrate, and each of those particles has a 1 negative charge. And we need for this equation, which is looking at just the charges now, we need the equation to work out to be 0. We want a neutral compound because up here there is no charge listed on the end, so it must be neutral. Okay? The only number that works out here is for this to be a 2 plus. Therefore, the charge on the lead must be 2 plus. And if it's 2 plus here, it's going to be 2 plus here. Now we got to figure out how to balance the formula. Well, if we have a 2 plus charged particle, and we're putting that together with some unknown number of 1 negative charged particles, we want this equation to work out to be 0. The only number that works out here is to put a 2 in front of this, which means I need 2 iodides. And then when I put the formulas together, or put the formula together for these 2 ions, or this set of ions, we get 1 lead and 2 iodides. So the formula then up here needs a 2 subscript after the iodine. Okay? Using that same process over here, we'll look at the charges that exist on the sodium and the nitrate and figure out how many of each of those we need. Well, sodium has a 1 plus charge. Nitrate has a 1 negative charge, we said already. So if we put those together, we're going to get a 0 charge. So we need 1 and 1 of those, and we can see that that's already balanced. Now our formulas are all balanced. And the rule is, once the formulas are balanced, leave them alone. Don't change any of the subscripts now. The only thing we can use now to balance the equation is a coefficient.